Hello and welcome to section 2.2b. In this section we are going to talk about zeros of functions and how they relate to the actual function that we're given. So on the first one it says determine how many real zeros of the following functions should have based on the degree and how many max and mins it could have. Now we talked about in the past that the highest degree is how many zeros it could have. It should have. So if you look at this one, the highest degree is 2, so it could have 2 zeros. And then the relative max, so n being the highest degree, the degree of the polynomial, and then the relative max and mins always are n minus 1, so the highest degree minus 1. So there should be 2 zeros for this one, and probably 1 relative max and min. Now let's think about this function. This is a parabola. It's upside down, so it should look something like this, which would make sense that there is only one maximum or minimum depending on the graph itself. And it looks like this one crosses the x-axis twice, so there would be 2 zeros or 2 real solutions. So over here we have a cubic function, and so in a cubic function we could have 3 real zeros because that's the highest degree, and if we do n minus 1 there are basically 2 possible relative max and mins. Now if I graph that, you can see that, well, it only crosses the x-axis once, so there's really only 1 zero. And there doesn't, since this one is increasing the whole way, there are really no max and mins. So these are what they should be and what they could have. It doesn't necessarily mean that's what's happening, because in this case there's really only 1 zero and no max or mins. So it just kind of depends on the graph itself, so always get a picture of them would be helpful. And so then this guy right here, there should be 4 zeros, 4 places it could cross the x-axis, and 3 relative maximums and minimums. And when you look at the graph, well, this is a zoomed in graph of it. You can see that it looks like it only crosses the x-axis twice, and the relative max and mins, there's only really one of them. It doesn't, I can't zoom in enough to make it look like the W shape that it should be. So that one, even though there should be 4, there's actually only 2. And in this one there should be 3, but it looks like there's only 1 in this case. Now I didn't graph this one, so if you want to see what it actually looks like, you should graph it. But it could cross the x-axis 10 times, and it should have 9 relative maximums and minimums. Now that doesn't necessarily mean that's what it is. As you've seen in B and C, that's not what actually happened. A is the only one that actually matched up with what it should. So please pay attention to these. These are just guidelines to what could or should happen. So then some of these are because we have what we call repeated zeros. And basically when we get a factor and we have an odd power, so going back, when we're talking about an odd power, that would be like 3, 5, 7, 9, those guys, then x equals a, it's going to cross the x-axis. So if I go back to this guy right here, I will have 3 factors that are basically the same because it's only crossing. When I look at my graph, when I look at my graph, that is where it's crossing. So this is what we're talking about with our odd function, is that it crosses the x-axis at x equals 4. If we have an even function, if k is even, the power is even, then we could end up with having it just come down and touch the x-axis. So here's an example of an even function, x minus 3 squared. The factors implies that it would be x equals 3, and since it's a power of 2, that's 2 times. And so when I look at my graph of it, here's the graph of it, you can see that it doesn't cross the x-axis, it only comes down and touches it. If it was an odd power, then it would cross at x equals 3, and that's kind of what we're talking about for these guys. So please make sure that you can see that it's touching the x-axis and it doesn't cross it. If it was something else, it might cross it. But so we're talking about the multiplicity, and it's just getting the same factors over and over and over again. Will be how it crosses, how it just touches for an even power, it'll cross for an odd power. So make sure you get that down. So then it says find all the real zeros using a graphing utility. So what I did is I graphed the function here, and so then it says what are there are only 3 real zeros, and you can see them, 1, 2, 3, and it says should there be more? Well, there could be up to 5 of them. And if we want to actually find those real zeros, here's my graph. I'm going to go to second trace, and I'm going to get rid of the, get rid of this stuff. Second trace and find a 0 value. And I'm just going to, I'll do one or two of these. I'm not going to do all of them. But below, to the left, to the right, and then a guess about where it might be. And so one of my zeros, even though it looks like it's at -2, is at -1.86 and 0. So then the other one, which looks like it's at 0, I'm going to do second trace, find the 0 value, which remember these guys are also roots and solutions, so left of it, right of it, and a guess. And so there's another solution, there's another 0, and then the last one, might as well finish it out. I know I said I wasn't going to do this, but I might as well. To the left, to the right, and a guess. And so there's my other one. And sometimes you'll get this to happen, that when you look at it, you'll see that I get like 1.4 e to the -12, so that's basically 0. And so that's really all I'm looking for right there, is that this could possibly. So you get a 0 for this, so the other one is that. And so then some of these guys could be, if we went through and figured it out, some of these guys could be, there should be 5 solutions, but as you can see there's only 3 solutions for this graph. And basically it could be a multiplicity, it could be an imaginary root, just depends on the factoring of this function. And so we're not really going to factor it right now, we'll do that, save that for another day. So then our final one, it says find a polynomial function with the following zeros. There are many correct solutions, and so we talked about this the other day, that these guys are my solutions. So x equals a -1/2, x equals 3, and x equals 3. So if that's the case, those are my solutions, then I'm going to solve each one of these so that x equals 0. So I'd say x plus 1/2 equals 0. And then this one would be x minus 3 equals 0, and x minus 3 equals 0. So what I did, if you guys don't remember, is I just subtracted 3 across the equal sign for each one of these guys, and over here I added a 1/2 so that I would set this equal to 0. And so these are our factors, because if you look at this, I'm just working backwards to undo the equation that we solved. So these guys would all multiply together to get me 0. If I do x plus 1/2 times x minus 3 times x minus 3, we could say those are equal to 0, and we break it apart. Remember, once we get a function factored, we set them equal to 0, we break each part equal to 0 by the zero product property. And so that if you kind of look, by the time I'm done, if you worked this way, if you worked up what I've done, you would have solved for x. Now I'm going the other way, so I'm putting it back together to get an equation. So I'm going to do one little trick here just to get rid of this fraction. I'm going to multiply this thing by 2. Just this part, probably could have done it here. I probably should have multiplied by 2. That would have gotten rid of my fraction. And by multiplying that by 2 in that equation, I'm left with 2x plus 1. It's just trying to deal with fraction. But if you would have left the fraction in there, it would have been fine. It wouldn't have mattered. So now I have to multiply these guys together. Well, x minus 3 times x minus 3, since they're the same thing, well, okay, so let me back up a second here. We could write our function like this, and that's probably okay if I put an a value out front, and this is why there are many correct answers. Since these guys are the solutions, we don't know what a is. We would need to find some ordered pair to solve for a, have an x and a y, and so we don't know what the actual solution is. I could multiply this all out if I wanted, or you could probably leave it like this and it'd probably be okay. But if I multiply it out, let's just multiply it out to practice a little bit. And so I have 2x plus 1, and I'm going to multiply out x minus 3 times x minus 3. Remember that you have to distribute, so I'm going to take x times x minus 3, and then -3 times x minus 3. And so that's really my way of multiplying these guys together. So I'm taking the first x times x minus 3, and then this -3 times x minus 3. And by multiplying that out, I get x squared minus 6x plus 9, and I just kind of multiplied them together as I did it and combined my like terms, and that still equals f of x. And then finally I have to distribute my 2x, so it's going to be a, and then it would basically be 2x times that term, x squared minus 6x plus 9, and then plus 1 times x squared minus 6x plus 9. And so that's just my multiplying that out. And so I'm using the distributive property to multiply those out. And so I will continue on, and the original function that I probably would get would be something like this: 2x cubed minus 12x squared plus 18x, and then just repeat what I have there because I'm multiplying it by 1. And so really the only thing left to do is to combine my like terms, and so it's going to be some a value times, well, 2x cubed, and then I'm going to cross out so I keep track of what I've done here. I've got negative 11x squared, deal with my x squareds. I've got 18 minus 6, which gives me 12x, and then plus 9. And so there is the function that if I factor it, I will end up with my solutions of these guys. And the a value in this case could be 1. We don't know what it is. It could be any number, but we don't know exactly what it is yet. But this is the generic form of the function that we're dealing with. So we've practiced this, and so remember that if I go from this part and work backwards and factor, I end up with these solutions. If I have the solutions, I can just work the other way by multiplying them together to get the equation that I'm looking for. So if you have any questions, please come to class prepared to ask them.